fx, rx, qx, and dx. And what is a here? By the definition of a partition function, it is the integration of px dx. And we can do the similar trick. P prime x divide qx multiply qx dx. And this is rx. This guy here is rx and qx dx. So we plug in the definition of a to here. It will become fx rx qx dx over rx qx and dx. And here, look at here. This qx is a distribution, and here is a function of x. So this is simply the expectation of fx and rx defined over q. We put a subscript q here, means that the expectation is computed with respect to q, distribution q. And similarly, here it is expectation q of rx. And we know how to draw many samples from q. So we can use the sample mean to approximate this expectation. Suppose we draw capital M samples from xi equals to 1 to capital M. All of them are drawn from the distribution Q. So given this set of samples, we can use it to approximate the expectation. 1 over M, sum over I equals to 1 M, f xi r xi over 1 over M, I equals to 1 to capital M, r xi. And the 2M cancels. So you can use this, plug in the samples into this equation. You get the expectation of fx. And here, we didn't reject any samples. All the samples generated from Q are utilized. And we plug in the samples into this equation, and we get the here should be a approximate. We get a approximation of the expectation of fx. And remember, Rx is defined as this, and the Px are known, and the Qx are known, so you can easily compute the Rx. Any questions about the derivation? Okay. You mean here? You mean this equation? Okay. This equation. Did you actually did Barnabas cover graphic model in detail on Markov random field? No. Oh, that's why. Okay. I'm not sure whether we have time to elaborate this. So let's say this is a graphic model containing 3 random variables, x1, x2, and x3. And we say let's use x to denote x1, x2, and x3. And x is a vector. We say px vector is proportional to the probability of the 3 variables is proportional to some function you defined. Let's say p prime x vector. And this function can be any positive function. If you believe the proper given a x star, if you believe px star is large, let's state it in this way: given an arbitrary vector x star, if you believe p prime x star vector is big, then it implies px star vector is the probability of x star vector is also big. And this function is defined based on the knowledge you have over this problem. And this function reflects is kind of proportional to the density of the true distribution. And to make this into a probability, we have to normalize it to ensure the integration of it is 0, is 1. And z is defined over the integration of p prime x vector dx vector. Basically, given any configurations of x vector, you sum them up. That gives you the z. But in reality, this quantity here is really hard to compute. By contrast, this potential function here is easy to evaluate. So that's why in these examples, we are discussing this kind of distribution because they are used a lot in practice. I know it's kind of hard to understand this without a detailed introduction of the Markov random field. Let's simply assume this. The distribution is defined in this way, and p prime x is easy to compute, but a is very hard. Any other questions? So although all the samples generated from Q are accepted in important sampling, but the problem is, let's still use this graph. Remember the expectation of Pfx in important sampling is approximated by gamma xi is defined as p prime xi over qxi. in importance sampling, the two equations are like this. So let's say if the true distribution again is two model distribution like this, and the distribution Q you choose as a Gaussian like this. So also in this region, the value of Qx is really big, but the value of pi x is really small. So look at this Rx here. Px is small and Qx is large, so Rx is very small. So its contribution, because in the sample mean all the samples fx all the values of fxi are weighted by Rxi. That means you generate a lot of samples, but most of them are given very small weights. That is in other words, you are generating a lot of unimportant samples. And their contribution to this expectation is very small and even can be neglected. So that's the problem of importance sampling. In practice, it's very hard for us to find a Q which matches well with P. Match well means if you choose a Q like this, it matches pretty well. But in practice, it's hard to do this. And sometimes in most cases, we don't even know what's the shape of this target distribution. In that case, you cannot even decide a Gaussian is better or multinomial is better. So if, unfortunately, you choose a Q distribution like this, most of the samples generated here are given low weights, and their importance are underestimated. So this is the drawback of importance sampling. It's pretty much like rejection sampling. In rejection sampling, you take a lot of efforts to generate many samples here, but most of them are rejected. And for importance sampling, although you didn't reject any of them, but most of the samples are given unimportant weights. Yes. So if this is the true distribution, pi x, and you are lucky to pick a Qx in this way. In this case, because the density of Qx, these two regions are high, you will harvest a lot of samples in these two regions, right? Because all the samples are from the Qx. And because Qx and pi x matches well, which means that the density of pi x in these two regions are also high. And if you look at this equation, this weight is pretty much like 1, because these two values are very close. That is to say, you give a lot of attention to most of the samples you generated. And with the samples generated here, you can get a very good approximation of the true expectation. Any other questions? The first line to the second line? The second line is the integration on the denominator is about alpha, about a. A is, remember, the definition of a partition function is the integration of the potential function. So this is p prime x qx divided qx and dx, and here this is rx. And because a is on the denominator, so that's why. Okay. Okay, let's go to the MCMC sampling method. Let's summarize again the disadvantages of rejection sampling and importance sampling. This is the true targeted distribution we are trying to get samples from, PAX, and this is QX. It is let's say a Gaussian. The problem with these two methods is because all the samples are first obtained from QX, and the density of QX, the highest density of QX is in this region. So we are going to generate many samples here. However, for this for the target distribution PAX, the density is very low, and this will cause the problem. In rejection sampling, most of the samples here will be rejected. In importance sampling, most of the samples here are not given enough attention and not attached enough importance. In other words, you try your best to generate many samples from Q, but discard or underuse most of them. The essential problem of these two methods is it's very hard to find a Q which is whose shape of the density is more or less similar with the true distribution, true density. So this motivates the idea of MCMC sampling. Instead of using a fixed Q, we can use adaptive Q. Adaptive Q means during the process of sampling, we can change Q with time. So in time t equals to 0, we choose a Q1, Q0. In time 1, we choose another distribution, another Q1, like this. So the basic idea is to replace the fixed Q with adaptive Qs in the process of sampling. And MCMC methods, usually there are two methods, actually one method. The first one is called Metropolis-Hastings, and another one is Gibbs sampling. Gibbs sampling is a special case of Metropolis-Hastings. So here is the how we choose. Here is the idea in MCMC. Suppose we get a sample X. We already get a sample X, and we want to generate a new sample X prime. How can we sample X prime? we are going to sample x prime from a distribution parameterized by x. Let's think about the Q as a Gaussian distribution. In time t equals to 0, I sample x0 from a Gaussian distribution whose mean is 0 and the variance is 1. And in time 1, I'm going to sample x1 from the Gaussian distribution parameterized by x0. Let's fix the variance to make things simple. And in t equals to 2, I'm going to sample x2 from a Gaussian distribution parameterized by x1. So you see, in each time step, the distribution Q is changing. In time 0, the mean is 0, and in time 1, the mean is x0, and in time 2, the mean is x1. That's why we say the Q is adaptive, and why we call this method Markov chain. Because the distribution Q in time 2 depends on the variable in time 1. It's kind of like a chain that the sample from in time t only depends on the samples in time t minus 1. See, it's kind of like a chain in this style. And Markov means the first order Markov means t only depends on t minus 1 and has nothing to do with all the variables from 0 to t minus 2. Okay.
In your example of the multimodal distribution,
Mm.
you are still likely to jump between two peaks.
Yeah. So in this two-model distribution, if you fix Q to a single Gaussian, the shape is like this, and it is fixed, cannot be changed later. But if you use adaptive Q, at the time t, the Gaussian might be like this, and t equals to 1, it moves to here, and t equals to 2, it moves here, and 3 moves to here.
You also have another peak.
Another peak, you mean here, and you can also move back. Yeah. Yes, you can. The adaptive Q can move in between these two peaks.
But if you jump between peaks, your xi still likely to give very small importance.
Why is that case?
Because in that case, below that peak, the distribution, your QX, the probability of your QX is
I think you mean. So this is the targeted distribution. In some times, the Q will be here, right? And in this case, the samples generated from here will be given low importance. That's what you mean. But since this Q can move around, it cannot stay here for a long time. After several samples, it can move to other places, like here or here. Yeah, there is still some possibility that the samples you generated will be given low importance, but there are a few, not too many. So the MH sampling method is also very simple. It has 2 steps. So first, you suppose X. Let's say I'm going to generate X new, a new sample from a Q distribution parameterized by X old. I generate a sample in this way, and next I'm going to compute a quantity X X new given X old, which takes a minimum of 1 and px new or px old. Basically, this equation here. That's simply the two steps in MH sampling. Given the current sample X old, I'm going to use the distribution Q parameterized by this X old to generate a new sample X new, and after this step, we compute this quantity, which is defined as the minimum between 1 and this quantity. And the P distribution here is null, so you can plug in the value into P, and also X old into P. And the Q is also null, so given these 2 values, you can get a number. And similar to rejection sampling, we are going to use this quantity here to decide whether we accept this X new or not. If we don't accept it, we generate another sample from this Q X old and charge again. If we assemble X new, we are going to replace X old with X new and move to the next step. Any questions about MH sampling? You might be kind of confusing by here because I said before Px is hard to compute by P x prime is easy, and there is a normalizer here. Look at here, it's a ratio, so you can cancel Px prime, Px. If you do the ratio between them, you can cancel the partition function, and this guy actually becomes P prime x new over P prime x old. And the P prime is easy to evaluate.
Can you get more than one probability, more than one value for this ratio? Where we are doing this minimum?
Minimum because we want to make sure that this guy here can be larger than 1. Yeah, so we want to take the minimum to ensure, because here it's a probability. Yeah.
But can the entity be greater than 1? That's what I was wondering.
Which one is 1?
That ratio can be greater than 1.
Yeah, it is possible. If it is bigger than 1, you can. So A becomes 1, right? Yeah. So if it is less than 1, A is that quantity. Because A here is pretty much like the accept probability in rejection sampling. And here is an example. So starting from x0, this red curve is a distribution Q. it is a Gaussian.